Okay, so welcome everybody. This is now the second lecture by David Stern within the framework of the Francqui Chair at Hasselt. So the title of this week's lecture is Energy and Economic Growth and Development. So we are now trying that you can ask your questions throughout the lecture. You can do that by typing your questions in the chat, or you can also raise your hand. There is a raise your hand button at the bottom here in the Blackboard window, and then David will directly react to your comments and questions. And I would also like to emphasize here the upcoming lectures. So next week will be a lecture about the rebound effect. And then after Easter, we have 2 lectures in April, one about the Industrial Revolution and one about the econometric modeling of climate change. So with respect to GDPR, it is important now that I emphasize or mention that this lecture is recorded and it will be later available online. So by staying with us, and please do stay with us, you agree with this. Okay, so the floor is yours, David. I stopped sharing my screen now.
Oh, you started the recording?
Yes, the recording started, yes.
Okay, let me try to share application. Select this, allow. Okay, I think we worked out now that I've got the cursor in the right place and everything. Okay, well, welcome to the second lecture. Thanks for coming. So the first one I talked about economic growth and the environment, sort of broad topic, and went from some more general things to more technical. This one also sort of starts quite general, goes to more technical at the end, and just maybe things that I'm sort of got questions about really at the end, which will be sort of following on to next week's third lecture. And yeah, this one is looking now, rather than the impact of economic growth on the environment, it's looking at the role of energy in economic growth. And it's not totally clear here, of course, whether it's sort of growth that drives energy use or energy use drives growth. They sort of move together and they're connected. We will be asking, though, the question whether energy is a driver of growth in this presentation. So let me try and clicking here works. All right. So roadmap of what I'm going to cover. Some very basic stuff about why energy is important right at the beginning, and then go on to basically look at a paper published in 2016 on sort of basic facts about the relationship in energy and GDP and development and so forth. And then paper published in 2014 was a meta-analysis of the literature about whether energy causes economic growth or not. And finally, some thoughts with a sort of simple theoretical model about what drove the decline in energy intensity. That's really an open question still. So it's going to be a bit smooth, sort of saying, well, maybe there's this, maybe there's that, and the evidence is a bit mixed. But yeah, again, we'll hear more about that next week. So starting off some sort of basic principles. What is energy? Well, we go back to physics. Of course, I'm not trained in physics, but I try to introduce some to ground the discussion in some biophysical principles. Energy equals the capacity to do work. And that implies that all the moving around and transformation of materials and heating and all these things we want to do in the economy require energy to do that. And what is work? It's when a force moves where a force acts on the body and moves in the direction of a point of application. Point of application moves in the direction of the force. So these are basic physics ideas. And the key thing, though, is energy conversion. To do useful work, you must transform energy from one form to another, from chemical in, for example, hydrocarbon fuel, into kinetic energy of expanding gas, and so forth. And so these transformations, as we'll see, tend to be one way, and that's why we always are needing more energy, and we can't really recycle energy as we can recycle many other materials. These are just units of energy, just to say that we'll see some units of energy in some of the slides. Usually we're using joules, going up from megajoules to gigajoules to petajoules, exajoules at the world economy level. And it doesn't matter which you use, whether you use those or British thermal units or tons of oil equivalent. All these are equivalent measures of energy. On the other hand, kilowatt hours are a measure of energy. On the other hand, watts are a measure of the energy per unit time. It's important not to get those mixed up. But key thing, people sometimes wonder, does it matter which units we use? It doesn't. As far as energy is concerned, these are all equivalent. More physics, laws of thermodynamics. So the first law of thermodynamics, conservation of energy. So in energy transformation, energy is neither created nor destroyed, it just changes form from chemical to kinetic and so forth. And the key thing here is that we don't create energy or produce energy in the economy. We have to get, energy isn't created. It doesn't disappear when we use it either, it just changes its form, but we have to obtain it from somewhere. This is a key fact about energy. And same in the course of the elements. A second law of thermodynamics, entropy, says that the entropy, or some sense of disorder of an isolated system, tends to increase over time. Of course, the Earth isn't isolated, it has energy coming in from the sun all the time. So we can actually have some local decreases some local increases in order at the expense of more disorder somewhere else. But of course, this is a general governing principle. So some of the implications in economics, we need to get energy out of the environment, causing disruption. There is less green energy and there's more green energy, but there's no totally green energy. Every sort of energy, including hydropower and wind power and so forth, involves taking streams of energy out of the environments to divert them to human uses, and of course, in practical terms, installing infrastructures to do that. But yeah, there are better and worse energies. One maybe measure overall of environmental impact is the amount of energy we use, because we're using energy to move things around, to transform materials and so forth. And so we're doing work on resources, we're doing some sort of disruptions to the environment. So sometimes you see people say, we should only worry about fossil fuels, not renewable energy. And I would say, well, maybe fossil fuels are worse, but they're not totally green. We got some questions here. I can't see the questions, though I can see there's a bubble with 3 attached to it. Stefan, do you know how I see the questions?
Yes, I think it's just I wrote something in the chat. So to emphasize
you wrote something.
Where you can find the slides.
All right. Okay, so I'll watch. If it gets above 3, we'll do something about it. Okay, so this is a diagram from a textbook, and often in economics textbooks we think about production in firms, consumption in households, and some sort of exchange going on between them. But that is only, of course, part of the total picture. This shows the square thing actually is the Earth. It's a square Earth here. And the economic system is just a subset within that larger overall system. And there are flows of resources. They can be temporarily stored in the capital stock. Though that capital stock doesn't last forever, it has to eventually be, it wears out and has to be replaced. And so there are flows of wastes back into the environment. Also, there's recycling that help reduce some of that, but inevitably we take resources into the system, then some waste by mass balance has to come out of out of the economic system back into the environment. The environment plays various roles here, but one of the key ones, of course, is the energy flow, which is coming into the planet from the sun and going out back into space. And most of the energy we use comes from the sun, either directly or indirectly, through being stored in fossil fuels, apart from nuclear energy and the tides, geothermal. So the only real exceptions to that story. So I'm looking at the shared. Okay, so that's the idea of extracting energy from the environment. There's some disruption, also the same with material flows. And that's why energy is important. Why energy intensity or efficiency might be important purely beyond thinking about climate change. Okay, it's an environmental issue. There are minimum energy requirements for transforming materials. So in that sense, you can't have endless gains in productivity if the things that people value involve materials. And of course, the service economy maybe is a immaterial than manufacturing industry, but it's still supported by these infrastructures of computers and buildings and communications networks and the energy flows that support them, or transport and so forth. So there is no economic activities that don't actually, in the real world, require materials and require energy for moving those materials around. And so if thermodynamics sets minimum amounts of energy required, then productivity can't increase indefinitely in that sense, unless we start to value something that's totally immaterial. We do to some degree, but there are limits. But there always needs to be a base of food supply and shelter and these things. And this is from about 15 years ago, but shows flows of energy in the world economy from crude oil, coal, natural gas, hydropower, nuclear, biomass, and so forth. A lot of the fossil fuels and so forth are transformed to electricity, with a big loss of energy, more energy lost than actually coming out. And then these flows come to the final, when I do this, I get this thing in my way. Comes to the final energy use sectors. That's better. Residential and commercial. I don't know how you hide that entirely. Industry, transportation, feedstocks. And this diagram here is reflecting the efficiency with which energy is used in those final sectors. And according to this analysis, industry is the most efficient, and that makes some sense because the profit motive has been driving efficiency gains in industry over a long time. And so the potential for further gains there is relatively low. There are more potential for saving energy in the residential commercial sector, and particularly in transportation. Transportation is very inefficient in the way it converts energy into actual useful work. A lot of waste heat, and a lot of moving stuff around that doesn't really need to be moved around. Okay. Creation, this is something the same with the extraction idea. Creation of water requires greater disorder somewhere else. It's good when we use the sun as our fusion reactor and have a lot of disorder in the sun versus having more of that on Earth, perhaps. But even so, capturing the solar energy requires some disruption. And the final one is that capital stocks don't last forever. There's a general tendency towards entropy and the degradation of materials. And so some economic models that try to solve the sustainability problem by proposing, well, we could replace natural capital with manufactured capital. That manufactured capital isn't, in the real world, a once-off investment of a non-renewable natural capital into manufactured capital. It requires continual maintenance by natural capital. So So if you depend on non-renewable resources, you really do have a problem. You need to try to depend on renewable resources or recyclable resources to the extent as possible if you want sustainability of the economic system over time. Okay, so that's just some basic things why energy is important, both for environment, and for maintaining our economic system, and why it's a subject worth studying beyond. People often just equate it with with concerns about climate change. So that was sort of the introduction about the importance of energy. And then I wanted to go on to look at this paper we published in 2016, and with Susanna Cireclii and Mar Rubio, who Mar is an economic historian, Susanna is a energy economist who was working for me as a postdoc, and published this paper in the Energy Journal. And we just want to see what are the basic facts about energy and the economy, which are fairly consistent across countries and time. Where's the word stylized facts come from? Economists tend to be familiar with this. It's used often in the, it's used quite widely across economics, particularly in the economic growth or macro literature based on, I don't know, it seems like Kaldor in 1961 or 57 or whichever year it was, coined this term stylized facts. So it's not an absolute law of nature, it's more like a statistical regularity and some massaging of the numbers to try to get things to fit, but it's an overall pattern that our theory would have to explain. And really in the whole energy area, there's more patterns which nobody's really explained, I feel, than things that have been explained. So I think there's a lot of room here for theory to explain the patterns that we see. So the data we used, I've updated the data from our paper. Our paper, I think, only went up to 2010, and I've updated the data here to the most recent data available from the International Energy Agency and the Penn World Table. And historical data come from another economic historian, Kanda et al. Also one of my co-authors, a book called Power to the People, published by Princeton University Press. They gathered a lot of data for that book, the history of energy use in Europe over 5 centuries. And the others from a paper about by Mar about Latin America. So the first of these is there's a stable relationship between energy use and income per capita over past 50 years now. It was only 40 when we wrote the paper. Only reason we don't say it's longer than that is because we have data on far fewer countries before 1970 than we have after 1970. And this is the cross-section in 2018, the most recent one. And so we have here GDP per capita in PPP terms. And we have on this axis energy use per capita in gigajoules per year. And they're both log scales. This outlier here is Venezuela, which is going to be causing us some trouble in the last few years because its GDP as in the Penn World Table has become very low. But I wanted to include it because it was in our previous our published study, and it does upset things a little bit in this analysis. So what we see is if you have a higher GDP per capita, you have a higher energy use per capita. And China is this big circle here. I think these circles are the total energy use, and this is the United States, and of course India is this circle here. And hopefully, yes, I am drawing the cursor in the right spot. I'm in about 100 countries in the sample, which are all sort of spread down this curve mostly. But it's a log scale, so there's quite a lot of variation in the income level among countries. This country and this country both have a similar income, but have quite varying levels of energy use per capita, in fact, even though there's a rising tendency with higher income, which leads some people to say, well, we could use much less energy. Not sure that's a very practical policy proposal. If most countries don't, a few do. Now, the interesting thing we're going to see here, we're just going to look at this relationship I showed you for 2018. I'm going to show it to you for every year separately. And I'm not sure this is going to work. It's going to work. Yes, it's going to work like this. So we're just going to see it like an animation. I think you might be getting the point already. Whoops. So it is a remarkably consistent relationship over time, this relationship. The main thing that happens is most countries get richer, move towards the right, and as they move towards the right, on average, though there are probably exceptions, their energy use increase. But it's been remarkably consistent. And I was really very surprised when I first saw how consistent this relationship has been. So any theory about this has to sort of explain why it is such a consistent relationship. I don't think anyone's really fundamentally explained that yet. We look at this is the coefficient of the slope of each of those individual regressions, cross-sectional regressions over time. And again, it's with a confidence interval, but again, it's remarkably consistent over time. These last two are driven by Venezuela, moving off to the left. And we dropped it, Venezuela would be very similar to the previous years. And these are the intercept terms. So it's not, so we're seeing the slope being very consistent, and we're also seeing the curve is not really very much shifting down over time. It might have been a bit higher here than it was here, but these confidence intervals around this, well, these are annual confidence intervals, so they all overlap. So there's a pattern perhaps rising and then falling. We don't see a consistent pattern of like improving energy efficiency pushes down this curve. As I argued, technical change could push down the so-called environmental Kuznets curve relationship over time, but we didn't really see that for carbon emissions. And why we didn't really see that for carbon emissions is we haven't really seen that for energy here. The relationship not really systematically moved down over time, but there's some sign it may have done in the last few decades, but not in a statistically significant way. Okay. So very consistent relationship. So there's a constant elasticity of about 0.8. This implies that energy use increases over time. GDP increases by 1%. On average, energy increases by 0.8%. So globally, we're looking here, aggregate mean just means world energy use per person. So that's increased over time. And then the geometric one tries to look more at what happens in a typical country. The global is higher because there are a few big countries like the United States and China that are quite energy intensive. So it's higher than what's happening in the typical country. But both of those do go up over time. If we look over the very long span of history, going back to 1800 here, and for Britain, there's data from back to 1560 at least, if not earlier, being reconstructed. British GDP now goes back to 1270, I think. Broadbury data. We see energy use increasing in this sample of countries that have long time series. Of the United States here, we have Britain here, and we have Sweden. This is per capita. So the population also grew in all these countries. In Britain, the per capita has been pretty flat for a very long time. But Britain is somewhat is unusual in having been quite flat for a very long time, or even declined recently. The United States also has seen a per capita decline in this recent period after rising before that. And some of these countries have also seen flatter periods recently, or more generally increasing. There's some been very big increases. If you look at here, Italy or Spain, after the Second World War, they saw a very big increase. Less dramatic in these Latin American countries that we have data for, but pretty much the same thing happened in Sweden as happened in Southern Europe, and also to some degree in the United States in that period. And we look at this, Sweden, Spain, Italy, and Latin America were all quite similar back here when they all were poor countries. So yeah, there may be some flattening around here, or even declines in a few countries. Overall, though, there's been an increase over time. If we look, though, at energy intensity, it's lower with income and over time. So it's because the coefficient's 0.8, the elasticity of energy respect to GDP. So this shows income per capita again on this axis. This now shows energy intensity in megajoules per dollar. And that's declining. So if you're richer, you have a bit lower energy intensity. But again, there is a lot of variation across countries. And globally, there's been a decline. This is the global energy intensity, the blue line, and then the typical country. India actually follows this path quite well. There was about flat or increasing up to around then, and then sort of joined the larger countries after this period. So some countries did have a different behavior. And what they've done is they've tended to converge towards the larger countries over time. So what we see is that because the curve hasn't shifted down over time, you need really to, historically at least, to have economic growth in order to lower your energy intensity. So sort of the idea that stopping economic growth will, well, it would stop increasing energy use, but it wouldn't do very much for energy intensity. So this shows over a long, long period now, the average economic growth rate on this axis in income per capita, on this axis in energy intensity. Most countries are in this square down here, there is this rectangle where GDP grew, per capita grew, and energy intensity fell. And there are a few now which had all the ones that had declining GDP had rising energy intensity. But even within this box, there does seem to be a linear relationship. The faster your growth, the faster your energy intensity fell. Okay, that again, there's a lot of scatter. All right, so this seems a pretty consistent relationship. It has quite a few predictions. On the other hand, there's been a convergence in energy intensity over time. Countries have become more similar. And this one looks at energy intensity back 50 years ago, and then what happened to it over time. And the more energy intensive you were, the more you were to the right, the more faster your energy intensity declines. The very energy intensive countries had faster falling energy intensities. Well, some of those are countries like China and other formerly centrally planned countries. There's going to be some random reversion to the mean going on. Some people say, well, this is all reversion to the mean. But the effect is so big and consistent over time, it's hard to believe it's not something real and not just random. You had randomly high energy intensity for a while, and then you had randomly low energy intensity. It does seem like there's some real process going on, given the consistency over time of this relationship and the strength of the relationship. So energy intensity has converged over time. So these is Spain, Italy, Latin American countries down here. They've had pretty much flat, most of them flat energy intensity over time, whereas the more energy intensive countries up here have had more. Britain, United States and Sweden had more declining energy intensity over time, and so these countries have become more similar as time has gone on in terms of energy intensity. And yes, I think global economies are becoming more similar. Another interesting thing is this is these dots are 2010 energy intensity, and you can see apart from the United States in the early years up here, all these historical paths over up to 200 years are totally within this, this area of the energy intensity of countries in 2010. So it's not the energy intensity was very high in the past. The economy got very energy efficient, reduced energy intensity. These countries back in the 19th century had similar energy intensities to countries today at similar income levels. And this is going to, of course, be part of the evidence for the rebound effect, which we're going to talk in next week, that we don't really see any, we see this consistent relationship, and we don't see this, that today's countries are much less energy intensive than these countries were a century or more ago. Part of the United States is particularly exceptional up here. Another thing we've observed, but only for a few countries, is that the share of energy and costs of production falls over time. So it was much higher back here in the 19th century. This is Sweden. Share of energy costs in total costs in Sweden, it was very high. In Britain, this is on a macro level. In Britain, it was also higher than it is in the current today. So we see energy as a small share of the of total costs today from overall in the economy. That wasn't always the case, and it probably isn't the case in poorer developing countries today either. So these countries were spending a lot of their efforts on collecting energy, and that decline in that sort of energy requirement may have been one of the factors that helped them grow. But they used a lot of energy, and it was also a large part of their resources had to be devoted towards their energy production and collection compared to today. But yeah, we don't have this on the long term for many countries because prices haven't been reconstructed except for a few countries. Another fact is that energy quality. This is probably a pretty obvious one. The richer you are, the more you use more cleaner and more productive types of energy, like natural gas, oil, and primary electricity and heat. This is in 1971. These are whole world divided into 5 groups. Of course, the poorest people use a lot of biomass, and as you went to higher income levels, you started adding more of these more advanced, more productive types of fuels, primary electricity, natural gas. Coal is pretty constant over time. Updating that to 2010, we saw there has been some change in the natural gas is generally more available. Of course, this group here, that's the 5th quintile in 2010, is richer than any countries were in 1971. So since this whole graph has moved by about 1 quintile. So this shows a more advanced stage. You would get to the 4th quintile here to this one in 1971. And then I updated third to 2018 just for this lecture, and we see again a bit more change. Only a little bit of income growth, probably again more introduction of more natural gas in particular, taking a bigger share of. So there has been some actual change in that natural gas is more available. The world primary energy mix over time we look at this primary electricity. Heat's gone up, but it's been pretty constant since 1995. So in this early period, we're talking about hydro and nuclear primarily, but that share really hasn't increased even up to 2018, despite all the talk about the renewable energy revolution. Natural gas has gone consistently up. Coal has drifted around, went up, went down. Part of this shift towards China and India as part of the world economy. They were very coal intensive in this period from 2005 to 15, and now that's sort of stabilized a bit. And the share of oil has come down over this period, but replaced by natural gas and some degree renewables up till 1995. But little growth in renewables after 1995, so that sort of breaks what might be sort of common wisdom. Okay, whoops. So that is sort of an overview of the trends. So we saw in the first section that there is a close relationship theoretically between using energy and economic activity. And then we saw in this empirical, sort of descriptive empirical section, we saw that there is a very tight empirical relationship between your level of income of a country and its energy use, and some of the implications of that for energy intensity. And so now the next section would go on to ask, well, what is really going on here? Does energy cause growth, or is it growth causing energy? Okay. So this is really looking at another paper, which is a meta-analysis, was carried out with Stefan. Actually, the story of this is Stefan contacted me at the beginning of his PhD and was wondering about topics. This is one of them. But I said, well, there's this big literature and nobody's really analyze this literature. Maybe we should do that. And eventually we got to this paper also with Christian Gross as one of our other co-author. So we took this very, very large literature that tried to test whether energy causes economic growth or not, and tried to see, is there anything in that relationship or not, and what does this literature as a whole actually say? So if you look, sort of following on with the more sort of descriptive stuff, we looked at the relationship between just the level of GDP and the level of energy use. This one looks at changes, and we can see the whole world since 1990. We see this is the GDP here, growth rate per year over this whole period, and this is the growth rate of energy use. And so it does seem that it's not really just a spurious relationship, but the two just tend to increase over time together, because we see also the short run fluctuations are quite closely coupled. And even here there's a bit of an opening gap, but we do see that there is a coupling to some degree between the fluctuations in GDP and the fluctuations in energy use. So this doesn't tell us which way the relationship goes, but does give us the idea that it is more than just purely that two things are trending up at one's trending at 1% relative to the other one at 0.8%. Energy intensity has done this over time. So this looks like a big opening gap here, but actually when you look at this, it's just, maybe it's just a bit longer period, because if you look at the minimum of the best improvement energy intensity here, it's not that different to this one back in 1997. So maybe there's a few more years of particularly good energy intensity performance in this period. And then the most recent year, 2018, is not quite as strong energy intensity performance as the previous years. So it's hard to say that there's a change in the relationship happening. There certainly looks like there's some sort of real relationship between these variables. So looking at this big literature, it's a big literature. Started with paper by Kraft and Kraft back in 1978. They did a Granger causality test between energy use and GDP. And when I wrote a paper on this, one of the chapters of my PhD published in 1993. And so there weren't many papers back then. But then there are just hundreds. You can see here, this is the folder that Christian, I think, well, actually it was on, we shared the folder we shared. One folder for each paper were being collected. As you can see, there were 480 something papers in this at that point in time. And this is like a decade ago. And that doesn't seem to be a stop in the number of people publishing these papers. And I'm always surprised when I see them published in good journals, given how many papers have previously been published on this topic. So it's a bit of a puzzle. See, this is 2012, so it's 9 years ago. 488 items, yeah. And that probably wasn't everything. Yeah, as I said, I'm guilty of adding to this literature back in 1993. This was one of my early published papers. So Granger causality testing, for those of you not familiar with it, it's a time series technique. It's got its downsides. It's often over-maligned, I think, by sort of microeconometricians. So basically the idea is that we have a vector autoregression model. We have Y here is GDP, E here is energy, and we regress them on the past values of GDP and energy. And we select a certain number of lags. And then there are tests. The null hypothesis that energy doesn't Granger cause GDP, and that can be found by restricting some of these coefficients, and vice versa. But GDP doesn't Granger cause energy. What does it mean? It means that when we look at the past history of GDP, does energy add any explanatory power to this regression that's not explained by the past history of GDP? The downside of this method is it doesn't include any contemporaneous effects, because it depends on a lagged effect. And so some people would argue the contemporaneous effect is big enough could be as big or bigger than the historical lagged effect, and maybe in the opposite direction. So that seems like unlikely in most cases, but it is a potential shortcoming. It doesn't deal with the contemporaneous impact itself. It seems more likely the contemporaneous effect is in the same direction as the historical one. The other thing is people complain that it's got emitted variables bias. Well, that all depends how many variables you include. Of course, there's a limit to how many control variables. So this problem here is there are only energy and GDP. Well, maybe there are other variables are excluded. So people try to add a lot of variables to this model to see whether that changes the results or not. And you'll see one variable maybe does, but other variables don't seem to have a significant effect in the literature. So when we look at this literature, and we looked at the, we didn't use all 500 papers in the end. We threw a lot of them out. We used basically a sample from them. And when we looked at these, our sample that I think still had about 500 tests in each direction. Does energy cause growth or growth cause energy? About 36% of the tests, does energy cause growth, rejected or null? And so they said energy causes growth. Okay, so this is more than 5%. So it sounds like it's not just that there's something actually happening here. On the other hand, the majority of tests didn't reject the null. And then in the opposite direction, we have a very similar number. 39% of the tests of GDP causes energy rejected the null. The majority didn't though, but yet it's bigger than the 5% level. So it's a bit ambiguous, like this whole literature, what is really the truth here. So we looked at 72 studies, 574 pairs of tests. We convert their various different statistics. We convert all those p-values into standard normal variables. And so this is set up so very significant thing. A low p-value means a big positive test statistic. Okay, so this is so we can it's got the standard normal variables have got nicer properties for using in regression analysis than the p-values. There's several biases in this literature that we found. Some we knew about, some we discovered in the process of this search. We know about publication bias. It's well known that things that studies that found significant results or coefficients in the right direction tend to be published and published in good journals over ones that don't. So something published in a good journal, an empirical study, that could be actually, it's one of the ones that found something that looked really dramatic and got published. Hopefully our journals are getting better at detecting that. There's probably reason to be skeptical still. This is a basic meta-regression model. I'll show you how it could detect whether there's genuine relationship or not. So for this relationship, if we take our test statistics, so this is an actual effect, a coefficient divided by its standard error. So the thinking here is, if there's a genuine effect, there is an actual, the coefficient has a value, whether it's positive or negative, okay? And that doesn't depend on how big our sample size is, the value of the coefficient. On the other hand, the standard error gets smaller and smaller as we have a bigger sample size or more degrees of freedom. So the test statistic actually should get bigger with if there's a genuine effect with a big sample size or more degrees of freedom. And so there's no genuine effect. We should expect to see something like this. All the test statistics are kind of in a cloud like this when we look at degrees of freedom on this axis, and there's no relationship in the size of your sample and the size of your test statistics. But if there is a real true effect, the bigger your sample, the bigger your test statistic, and it increases with the sample size. In that case, there's more warrants saying there is some genuine effect in the data. Okay, so plot all our test statistics. This is energy causes output. Well, it looks like a cloud, doesn't it? This is the degrees of freedom on this axis here. Even this big study, one outline big study using a very long time series, doesn't seem to look any different to the cloud in here or everything else. This is 1.65, so everything above this dotted line is significant at the 5% level. And there are a lot of excess significance here. A lot of studies found significance. We found 36% found a significant result, but it doesn't increase with the sample size. So it looks like this is just spuriously significant studies, and for some reason. Publication bias is one of them. This in the other direction, similar story. We also found that people often use very small time series, and there's a tendency to put too many lags in the model when you have a small series, which ends up with low degrees of freedom, which ends up with seemingly spuriously significant test statistics. So we try to control for that by including a number of degrees of freedom people used up by adding more and more lags to their models. And for emitted variables bias, we look at the interaction between degrees of freedom and control variables to see whether any of these make a difference to the results. So this is a bit simplified from the actual model in our paper. We looked at a test statistic here. This is the test statistic. So the bigger this is, the more significant the result. This is the degrees of freedom variable, which should hopefully find some sort of genuine. There's a genuine effect. This coefficient alpha 1 should be positive and significant. This is our control for the overfitting bias problem. And then we looked at control variables and methods. These are these variables here. And for each control variable and method, we have a different dummy, and we interact the dummy also with this sample size or degrees of freedom variable. And then we test, is this joint effect of sample size, degrees of freedom significant for this method with this control variable? Okay. That is actually a little simplified from what is actually in the paper. So the idea is to see, are there particular methods or particular control variables that matter? Because overall, there doesn't seem to be anything. So you have to dig deeper to see, is there any part of the literature where there actually is something? And this expresses as T statistics for energy causes growth direction here. And the growth causes energy direction here. We're looking at, though in the actual published paper, there are more different methods. These are just 3 particularly well-known methods. So methods that use co-integration models, methods that use traditional Granger causality tests like I showed you, and ones that use a so-called Toda-Yamamoto test, which controls for stochastically trending or unit root variables. So it's valid in the presence of those variables. So these are 3 different methods, and then there are different control variables. No control variables, including capital, stock in the regression, including the price of energy in the regression, including a time trend, and including labor or employment. So the idea of people might include capital or employment. They're thinking there's some sort of production function for GDP here, where there's energy, capital, and labor, and maybe we should control for those things when testing the effect of energy on the GDP. We found that people who used co-integration models, they got, when these seem to have some effect where the relationship, the test statistics get larger with the sample size, sign of a genuine relationship. Problem is that people here are really, researchers are screening for co-integration. So if they don't find co-integration, and they don't sort of proceed to model a vector error correction model or whatever it is. If they do find co-integration, they do. So they have this sort of hurdle to get over first. So maybe that's not so surprising that there are some significant results here for some of these variables. Well, for employment, it seems. And this is for no control variables. If you already passed this hurdle of finding co-integration between the variables. Okay, whether that means there's a real thing or not, I'm not entirely sure, because it's already biased by having to pass that hurdle. On the other hand, in the growth cause energy direction, we found that studies that include the price of energy as a control variable found those when you looked at that sample effectively of the data using these dummy variables, you found a genuine relationship between GDP and energy, in terms of GDP causing energy use, and it's when you control for price. And what does it mean? Well, if you've got GDP in your model, you have energy in your use in your model, and you have price in your model, where you've got income and price and use of energy. It looks like an energy demand function. Okay, so that relationship seems to be there in the literature. You can find an aggregate energy demand function where income causes energy use changes. Okay. These other variables, no, there didn't seem to be a significant relationship. You don't control for price. You need to control for price and see what in this relationship. Okay, so that seems to be the relationship that's there in the data, and a demand function, a dynamic demand function. So does this mean that I think that if you cut energy supply suddenly, it wouldn't have an effect on the economy? I don't think, and that's sort of some sort of exogenous intervention to reduce energy use would not have any economic effect. I don't think that's what this literature shows. I think that would have an effect. I think, of course, the GDP growth generates desire to use more energy as well. I mean, both these things are going on. So why is this relationship more elusive? And only if you pass already a hurdle of finding co-integration do you find something significant. Well, one reason is I think perhaps it's a hypothesis only, the effect of energy on GDP is small. We already said the cost share today is 0.1 or 0.05. It's a very small number. So changes in energy use have a small effect size. It might be hard to see these in the noise, especially most of these studies have short time series. On the other hand, the effect of income or GDP on energy use is somewhere around 1 to 1, perhaps. Maybe it's 0.8. Maybe 0.8 reflects the average of these two, some sort of weighted average of these two numbers. But it's quite large, so it's not surprising. It's easier to find that effect than to find the effect of energy on GDP. I don't think it necessarily means that the effect of energy on GDP is just not there at all. Other things you might want to control for that most studies haven't. There are different forms of energy, have different productivities. We already discussed this. Natural gas or primary electricity perhaps are more productive per joule of energy than coal or wood. Perhaps you need to control for that. I did in my 1993 study. It seemed to make a difference, but that's just one study of a fairly small sample. Another question is, why is energy use changing? Okay, if there's a price shock that reduces energy use, that is an exogenous negative shock on our economy. We should expect to see output fall as a result of this shock to the economy. On the other hand, if an improvement in energy efficiency reduces energy use, we shouldn't expect to see a reduction in the output of the economy from that. In fact, quite the contrary, we should expect the energy efficiency improvement increases total factor productivity of the economy and should increase output. So changes in energy use, some of them are because of sort of exogenous involuntary things that disrupt economic activity, or vice versa. The price falls and energy becomes, we use more energy as a result and more output, versus technological changes that may save energy and not actually good for output at the same time. So none of these studies are controlling for sensor technology, which is a very elusive thing to measure. So we're going to try and in my presentation next week, we do have a model where we try to control for technology shocks versus price shocks in the analysis. So that's another reason why I think people found it hard to find an effect of energy on output, even though obviously if there's a shortage of energy, it would have some sort of effect. Okay. So we saw energy intensity decline, and it declined quite consistently at sort of at least an aggregate level. What's really driving this decline in energy intensity? And these are sort of just some sort of thoughts. To decline consistently over time in leading economies. On the other hand, it's increased in some low energy economies. Most decomposition studies are trying to see what is similar to the chi identity I talked about and the IPAT identity I talked about last week. Decomposition studies have tried to decompose between changes in energy intensity within sectors versus shifts in the structure of the economy and so forth. Find that within sector intensity decline, so improvements in supposed energy efficiency within sectors, is more important than structural change. So we try and look at some of these things in a theoretical paper that's still unpublished, which co-authored was one of our PhD students, Akshay Shankar, who is now a postdoc fellow at the University of New South Wales. So this goes to, you'll see this production function show up again also when I talk about the Industrial Revolution. Well, it's similar to the production function, similar to this. So this is a so-called constant elasticity, a substitution production function. We have an output, Y, gross output, but from, so probably thinking this at an aggregate level, if energy use, E, labor use, L. So this model was fairly simple. It abstracted from capital, just looked at labor and energy. And then we have factors which, technology factors which multiply energy and multiply labor. So if AE if energy use declined and everything else was held constant and GDP did not decline, that would indicate there'd been an improvement in the in AE, or measure of energy augmenting technology. And there's one for labor as well. People more familiar in macroeconomic models are the one for labor. And this phi here is based on the elasticity of substitution. So it's sigma minus 1 divided by sigma is phi. So it's just a standard constant elasticity of substitution production function. Goes back to 1961 or whatever. 1956, I think the generalization was later. And so the assumption here is probably that sigma, the elasticity substitution in energy and labor and energy and capital is probably less than 1. So it's possible, but not that possible to substitute one input for the other while holding output constant. If that is true, that these are relatively poor substitute. I prefer poor substitute than complement as a term. Complement, I think, people talk about complementary inputs, but I think that's best when we're talking about the effects of price changes. So here, the substitution possibilities are lower, and I prefer to call this poor substitutability. So this phi is negative. If we take the derivative of this respect to energy, okay, that's the derivative respect to energy, and this is the first order condition standard from microeconomics, that price of energy is then going to equal its marginal product, okay? So what can we learn from that very simple relationship? Well, if we solve this for energy intensity, okay, E over Y is now energy intensity, we get this equation for energy intensity. As a constant, there's energy augmenting technical change, and it has a coefficient power up here, and there's a price of energy, and it has a power up here. it turns out that because phi is negative, at sigma equals 0.5, these two coefficients are equal, and they're both equal to minus 0.5. Okay. So that means that energy augmenting technical change, technological change improves the efficiency of energy holding, labor and energy use constant, and the labor technology constant as well, reduces energy intensity. It saves energy, ceteris paribus, holding the price of energy constant. But it doesn't do it one-to-one. It does it about half of the gain energy efficiency. Translates into energy intensity. So this already says energy efficiency doesn't translate one-to-one to energy intensity changes. So the actual change in energy efficiency are probably larger than the changes in energy intensity. And this will be important for our discussion again next week on rebound effect. And increased energy price reduces energy intensity, and that is just the standard demand relationship. So that is, you can just put Y over here and see the effective income is one-to-one, the effective income on energy use, and you've got basically a demand function for energy. Okay. Okay, so of course sigma was different to 0.5, but 0.5 sounds a sort of central value. We found the value of 0.67 in a study we did for Sweden over a 200-year period. A lot of data. That was a lot of data. If the price of energy is constant, energy augmenting technical change does lower energy intensity, but not one-to-one. If you have a Cobb-Douglas function, sigma equals 1, there's no effect of energy efficiency or energy intensity. So this, the most common production function used in economics, it would have 100% rebound in this simple model. No effective energy efficiency or energy intensity. So the smaller the elasticity substitution, the rebound. The larger it is, the larger the rebound. So energy efficiency changes to translate less and less, the more substitutability there is, less and less into energy intensity gains. Labor augmenting technical change, on the other hand, has no effect on energy intensity here. It doesn't appear in this equation. Okay, so it's all down to so if the world is as simple as this, these are the only two factors: energy efficiency and the price of energy. And GDP growth would increase energy use one-to-one if these two were held constant. So the question is what's really happening to price is one of the questions. And it's notoriously elusive to pin down what's happening to the price of energy. There isn't really very good, well, there are some proprietary data sets on energy prices. Publicly available commercial, non-commercial ones are pretty limited. Even so, a few countries have very long price series. So what happens to price is a key thing. Is it a driver of energy intensity? Is it been rising energy prices driving down energy intensity? I think we already covered this one. So these are just some thoughts about, well, what we just look at the data. What does that suggest about what has happened to the price of energy? We saw in Sweden and Britain, the cost share fell. So the price of energy, if it rose somewhat. It rose less than energy intensity was falling. If price, therefore, was a major driver of the change in energy intensity, it put some limits on both the supply and demand elasticities of price. It seems it's got a fairly small effect. Let's have a look at this US data. This is more to the point. So in the US, we've seen energy intensity do this since 1900. Okay, basically a bit of a plateau fall, then consistently kind of fall. Before 1900, it seems to have fallen as well. And the sort of actual average price, this does include animal feed, and using animals for power was very expensive. That had a steep fall here. And then sort of after the post-animal period, after 1930, when draft animals weren't important anymore in the US, well, energy price fell, energy intensity fell. When energy price rose steeply and energy intensity fell, so it doesn't seem like there's a strong shift in energy price and energy intensity over the long term. So that might put some constraints on what the relationship is. It doesn't seem. It seems to be relatively limited short-term or direct effect energy price. So the driver of energy intensity does seem to be improving energy efficiency. The gains in energy efficiency are probably a lot larger than what we've seen in energy intensity. Of course, the real-world model is much more complicated. There's structural change, there are all kinds of things going on, and so it's not just these factors. So it looks like there's a small role of energy price on energy intensity. We also saw that energy intensity falls across countries with economic growth. Does that mean is that because the energy efficiency improvements are correlated with labor augmenting technical change? So energy efficiency gains are correlated with economic growth in general. Again, these are all sort of research questions rather than things we actually have answers to. Most people just seem to be studying more range of causality studies rather than actually trying to pin some of these things down. There seem to be a lot of open questions, in my opinion. But maybe the world is really quite different to this simple model. There's certainly going to be some role for structural change. Okay, so yeah, basically a lot of things we don't know. And we'll look at the rebounds next week. The similar story, a lot of sort of unknowns in the picture. When we looked at, well, rather than just treating technical change as exogenous, what happens if we look at the incentives for technical change? So using a directed technical change model. We show that if the price of energy was constant, then incentives actually increasingly favor labor augmenting innovation, because labor is relatively fixed relative to energy use. Which kind of then there's a little bit of a puzzle there. Well, why is energy intensity decline sort of consistently as it has if labor augmenting technical change doesn't affect it? But energy augmenting technical change is slowing down, should slow down. Maybe labor augmenting technical change does affect energy intensity. Anyway, we also theorized on this model that energy augmenting innovation is faster in energy intensive economies like this. So some countries starting up here, high energy intensity, would have more rapid energy augmenting technical change, according to this directed technical change model, and therefore declining energy intensity more rapidly than the countries starting with low energy intensity. So you would see convergence, which is what we saw in the data. So some things follow the predictions of the model, things are a little harder to reconcile with the actual observed data. Okay, and that's just about it. I really left you more questions at the end than answers. Hopefully you've got some questions for me. So that's it.
Okay, so thank you very much, David. Are there any questions, comments? So while people are thinking, I have one. And
okay, good.
So as a kind of bottom line statement, David, so what would you think to this optimistic view that with more technological innovation, more technological change, that we can actually manage to decouple economic growth from energy use, and how is this related to climate change?
Can we decouple? Well, I haven't really up till now. Looking at the data, it's been a fairly consistent relationship. We did see some signs of maybe a bit of a flattening recent period. We've seen declines in energy use per capita in some slower growing economies. Can we decouple further? Well, I think if we sort of valued things which were less energy intensive, rather than the historical pattern of change, then there might be some I mean, depends what you mean by decoupling. Is the energy intensity falling decoupling? Energy use is still increasing with the rate of decline of energy intensity. So we're not seeing any sort of strong decoupling there. I think it would take some sort of fundamental change from what we've seen up till now to see a different pattern. Now, maybe it's very strict climate policy or something, if enacted, would cause that, just because it hasn't happened up till now. But it'll be a bit of a break from the past. So it's hard to you can do a simulation model, CG model or something to make the effect of a policy and claim it's generated something, and well, there's no proof it couldn't happen, but so I think it's a break from what we've seen before. If there was a fundamental decoupling, that globally GDP would be growing and energy use would be falling, let's say. The fundamental change.
Okay. So there is also one question in the chat now. Can you see that? I
can't see it.
If you click on the...
It popped up for a bit, and then disappeared.
You have to click on the lower right on this speed bubble.
Speed bubble? I did click, speech bubble. I did click on that. I don't see it.
Okay, so then I read it to you. So
I don't know why I don't see it.
It's a question from
Oh,
Katerina.
I see it now. I need to click on the top of the page to get it. Got it. It's good to see that energy intensity is declining. So reducing GDP growth will reduce energy consumption. Would reduce the rate of GDP growth would reduce the rate of growth of energy consumption. So yeah, I wouldn't say it would. Well, it depends. Yeah, from what historically what we've seen, growth seems to be tied in the typical country with decline in energy intensity. Okay, so there's lots of different points here as I'm reading it. Okay, so what I'm saying is historically what we've seen is that energy intensity has typically fallen faster the faster economic growth happened. Does that mean that that is a causal thing, and or does it mean it's the only way to get reduction in energy intensity? Well, historically that's what we've seen, but if we had some radical policies that sort of changed that historical situation, you could get different worlds from the one we've seen up till now. So the fact that history's been like that doesn't mean that it always has to be like that. I think I don't think we understand enough to know to what degree policy can change that. Okay, so but we do. I mean, that's a pattern we've historically seen. Does that mean I think we should have economic growth to reduce energy intensity? I don't know that is necessarily reducing energy intensity per se is not that important as total energy use. Should we decrease energy use from where it is? Or we say should make it a bit more use it in a more environmentally friendly way, more environmentally friendly forms of energy. Should we decrease it from where it is? Well, I don't know. Political process really needs to decide that. So energy intensity fall on its own is not necessarily a good. The level of energy use is beneficial, but is disruptive as well. So there's always a plus and a minus to it. And what drives innovation? Innovation. The reason why we don't see a fall in energy intensity without economic growth is a bit of a puzzle, I would say. But I showed some sort of hypotheses with very simple models, but I don't see anyone following up on our empirical work and saying this is the theoretical explanation of what you found. So we've been struggling with this theoretical paper to try to work out some parts of that answer, but I don't think we have a good answer for that. Okay, seems like I answered that question. I'm sorry, a lot of my answers are we don't really know. I think there's been a lot of superficial research in this field, and theoretical models that make, but not very much like the real world. There've been a lot of models with sort of stocks of non-renewable resources that are being depleted and no renewable energy or something like that, or sort of where there's sort of an efficient depletion path and this and that, which are not like the real world. There are models that are like the real world, but there are a fairly limited number of them. In fact, theoretical models. So I think there are a lot of questions to explore still.
That's always good news for PhD students, right?
Yeah.
A lot of questions to answer. So are there more questions or comments? So if not, I think it's good to emphasize that next week is a highly, a very timely topic with the rebound effect. So it's a question whether we can actually reduce energy use when we increase energy efficiency. And I think David will present some interesting work on this, which will basically challenge this idea that a substantial decrease in greenhouse gas emissions can come from improvements in energy efficiency. So I think this is also a topic that is quite interesting if you are interested in climate change.
Mm-hmm.
Any last words from your side, David?
No, I think this sort of laid the sort of foundation to sort of go on to next week's presentation. Yeah.
Okay, then thank you to everybody, and
look forward to next week.
See you next week. Bye-bye.
All right. Okay. How do we...